Let's solve some problems together. So here's problem 1. So consider the matrices E equals 1 0 0 1, I equals 0 minus 1 1 0, J equals 0 I 0, and K equals minus I 0 0 I. And the problem is, show that Q equals plus or minus E plus or minus I plus or minus J plus or minus K is a group under matrix multiplication. Okay, at this point, I would urge you all to pause your video and think about this problem and try to solve it yourself. If you're unable to solve it yourself, then you can get some hints from what I'm going to do now. So what is it that we need to check to establish that Q is a group? So firstly, for a group, we need to know that we have a binary operation. So we need to check that multiplication of matrices is a binary operation from Q cross Q to Q. So we need to check that if you take any two matrices in Q and multiply them, you once again get a matrix in Q. Okay, so firstly note that if A belongs to Q, then minus A belongs to Q. So also, if you have minus A into B, this is minus AB, A into minus B is also minus AB, and minus A into minus B is AB. So we don't have to worry about signs. It is enough to check that if you multiply any two of E, I, J and K results in an element of Q. Because if you take the negative of any of these and multiply it with possibly the negative of another of these, you will still get at most an element of Q or the negative of an element of Q. So let's just look at these elements and figure out what their products is. So we'll make a little table here. We'll have X and Y, and we'll make a table of X times Y. And what can X and Y be? E, I, J, K, E, I, J, K. So here we're looking at E into E, that's spell E. I into E is I. E is just the identity matrix, right? Remember? E is the identity matrix. J into E is I. K into E is I. And similarly here we have I, J, K. Now what about I into I? Remember, I was the matrix 0, minus 1, 1, 0. So I into I is 0, minus 1, 1, 0 into 0, minus 1, 1, 0. And this turns out to be by matrix multiplication minus E. Okay, I will not do these explicitly, but you can easily also check that J into J is minus E, and k into k is minus e. Now what about I into j? So what was I is 0, minus 1, 1, 0. And what was j? Well, j was the matrix 0, I, 0. And this is, you can check, minus I, 0, 0, I. So that's k. So I into j is k. And similarly, you can check that j into k is I. I will not do it explicitly for you. And k into I is j. And likewise, you can check that j into I is minus k. Oops. I'm sorry. J into I is minus k. J into k is I. And k into j is minus I. And I into k is minus j. So this is the multiplication table for the elements E, I, j and k. And from this, it follows that Q is closed under multiplication. Okay. Now what are the other axioms? We have the axiom of the identity. So E is the identity of Q because it's the identity matrix, is the identity of multiplication. Okay, and multiplication is associative because matrix multiplication is associative, so we don't need to check it again. Oops. Matrix multiplication is associative, so Q has an associative product. What else do we need to check? We need to check the axiom of the inverse. So what about inverses? So from this table, we can figure out various inverses. So let's just write down the inverses of E inverse. Well, that's just E. Okay, what about I inverse? Now notice that I into I is minus I. So I into minus I is going to be E. So this is minus I. Similarly, J into J is minus E. So J into minus J is going to be E. So J inverse is minus J. K inverse is minus K. And if you have negative, then the negative of I inverse is I. So these are mutually inverse pairs. And so this makes sure that each element of Q has an inverse. And hence we can conclude that Q is a group. Q satisfies all the group axioms. These multiplications jk equals I, ki equals j, and ji equals k, ij equals k, these must look familiar to you. These are the relations for quaternions. So this group Q is called the quaternion group. Let's move on to problem 2. What are the orders of the elements of Q? Let me remind you that Q is the group consisting of 8 elements plus or minus E, plus or minus I, plus or minus J, plus or minus K. And I'll let you think about this yourself. So pause your video and try to solve this yourself. And if you cannot, then go ahead and watch me solve it. Okay, so we need to figure out the orders of the elements of Q. There are 8 elements. Let's just figure it out. So what about the element E? Well, E is itself the identity, so order is 1. Okay, now let's look at the element I. Okay, so then I squared is minus E, I cubed is minus I to the 4 is 1. So I has order 4. What about minus I? Well, minus I squared is also minus E, minus I cubed is I, it's minus of minus I, and minus I to the power 4 is 1. So minus I has order 4. Exactly the same reasoning holds for J, because J squared is also minus E. Remember, we computed this earlier. J into J is minus E, K into K is also minus E. Plus or minus J plus or minus K also have order 4, and that only leaves the element minus E. Well, minus E squared is E, so minus E has order 2. So after this we can make a table of the elements of E and their orders. So E has order 1, minus E has order 2, plus or minus I, plus or minus J, plus or minus K, all these elements have order 4. So our group has 6 elements of order 4, 1 element of order 2, and 1 element of order 1. Problem 3. What are the conjugacy classes in Q? Okay, and just to make this easier for you, let me remind you of a calculation we did earlier. This is the product of the elements I, J, K, and E in Q. You can pause your video now and try to solve this problem. And if you're unable to solve it, well, you can come back and watch me solve it for you. Okay, so let's solve this problem. So firstly, let's take the element E. What is the conjugacy class of E? So I want to know what is, if I have an element X in the group Q, X, E, X inverse. Well, I know that E commutes with all the elements of the group Q. So this is X, X inverse E. E is just the identity matrix, so it's in fact just X inverse, but that's just X, X inverse E by associativity, and so that's just E, because X into X inverse is E and E into E is also E. So no matter what X you take, X, E, X inverse is E. So E is a conjugacy class. Singleton E is a conjugacy class. Okay, The same works with minus e. X minus e x inverse. Minus e is the negative of the identity matrix. It commutes with all other matrices under matrix multiplication. So this is the same as x inverse minus e, and you're going to show that it's equal to minus e. So minus e is also a conjugacy class, a singleton conjugacy class. Okay, now let's think about I. So I want to know what happens if I conjugate I by various elements. So now if I take E inverse, well, that's just E is the identity element, so this is just going to be I. So there's not much use trying to conjugate by E. Let's just worry about what happens when we do J inverse minus J inverse and so on. So let's look at J inverse is equal to what? Okay, so for this it's convenient to use the following identity, which we can observe from this table. Ji is equal to minus ij, and then you multiply both sides by the matrix J inverse, you get J inverse is equal to minus I. So J inverse is equal to minus I. So certainly minus I is in the conjugacy class of J. What about J inverse? Not J inverse. What I mean is, what about K inverse? K inverse. Well, with the same kind of reasoning, you would have Ki is equal to minus Ik, and so Ki inverse is equal to minus I. So this is also minus I. And what if you do instead of J, you take minus J? Minus J minus J inverse. Well, minus J is minus of J, and minus J inverse is minus is J inverse, the negative of J inverse. So this is again going to be minus I. And similarly, minus Ki minus K inverse is minus I. So what we have is that I and minus I is a conjugacy class. Similarly, J comma minus J is a conjugacy class. Just follow the similar kind of reasonings. And K comma minus K is a conjugacy class. So, final answer, the conjugacy classes of Q are E minus E plus or minus I plus or minus J and plus or minus K. Problem 4. What are the subgroups of Q? Okay, once again, I'd urge you to pause your video and try to solve this problem yourself. If you cannot solve it, then you can come back and watch me solve it. Okay, so we need to figure out what the subgroups are, or subgroups of Q are. Now, there's always, remember, Q has 8 elements, plus or minus E, plus or minus I, plus or minus J, plus or minus K. And in any group, there's always one subgroup, which is the trivial group. So E is itself is a subgroup. Why? Well, it's a subset of Q. It's closed under multiplication. E times E is E, and it's closed under inverse, and the identity is also in it. Okay, so E is a subgroup of Q. And you can also look at plus or minus E, because minus E into minus E is plus E, so this is again closed under multiplication, and minus E inverse is again minus E. So this is also a subgroup. Okay, what other subgroups do we have? So suppose a subgroup contains the element I. Okay, if S is a subgroup and I belongs to S, then surely I squared belongs to S and I cubed belongs to S. I cubed is minus I. So then minus I belongs to S because minus I is I cubed. Now you look at this elements E, I, minus E, minus I. So this minus E is I squared and minus I is I cubed, and then you multiply again by I, you'll get back E. So this is again a subgroup. Similarly, you have E, J, minus E, minus J is a subgroup, and E, K, minus E, minus K is a subgroup. So we have these three subgroups of order 4 corresponding to the elements I, J and K of the quaternions. Now suppose S is a subgroup which contains I and J. Then recall that Ij is equal to K, so K belongs to S. And minus I obviously belongs to S because that's I cubed, minus J belongs to S because it's J cubed, minus K belongs to S because it's K cubed, and of course E belongs to S and minus E belongs to S. So this implies that S is all of Q. So, and similarly, if a subgroup contains I and K or J and K or I and minus J, any such combination, it will be Q. So these are all the subgroups of Q. I like to show this in a somewhat visual form. So we have the smallest subgroup, which we'll write at the bottom here, E, and then we have above that the subgroup plus or minus E of order 2, and then above that we have three subgroups, E, I, minus E, minus I, E, J, minus E, minus J, and E, K, minus E, minus K. And then we have the largest subgroup of Q, which is all of Q itself. And these edges here denote that, this is contained in Q, this is contained here, and so on. So these are the subgroups of Q. Q has 1, 2, 3, 4, 5, 6 subgroups, including the trivial group and Q itself.